Hello, I'm Nicola Dinsdale from the Oxford Machine Learning and Neuroimaging Lab at the University of Oxford, and today I'm presenting our work, SFHarmony, Source-Free Domain Adaptation for Distributed Neuroimaging Analysis. Although some large-scale projects, such as the UK Biobank, exist, the majority of neuroimaging datasets remain small. This necessitates the combination of data from multiple sites and scanners, both for statistical power and to represent the breadth of biological variability. However, combining datasets across scanners leads to an increase in non-biological variance due to differences such as acquisition protocol and hardware. Thus, we need harmonization methods to enable joint and biased analysis of data from different scanners and studies. However, data cannot simply be shared across imaging sites without ensuring compliance with data privacy laws. Federated learning has been proposed as a method to train models on distributed data, where the data are kept on their local servers and the users train local models on their own private datasets and then share only the weights or gradients of the trained models. However, federated learning assumes that there is constant access to the source data, which is often unreasonable, especially for medical images, due to storage limitations and data privacy concerns. Thus, we need source-free methods for training models. Therefore, we present a new method for source-free domain adaptation applicable for MRI harmonization based on the alignment of extracted features via a modified Bhattacharya distance. We demonstrate that our method can be applied to classification, segmentation, and regression tasks without changes, and that the approach is robust to additional challenges likely to be faced when working with real-world medical images, differential privacy, and label imbalance. For SFHarmony, we assume a network formed of two parts, a feature extractor and a label predictor. These can take any form as appropriate for the task of interest. The aim is then to create a model which performs well as possible for a given target site, while having features which are invariant across the source and targets. We assume a fully unsupervised target dataset. The procedure is then formed of 4 parts. In step 1, the source model is trained. This can be trained as required by the source site, with no changes required. In this work, we assume a fully supervised source, but this is not necessary. In step 2, once we have a well-trained source model, we then create the information for the global knowledge store to allow the feature alignment. We cannot share the full features as these will contain a lot of information about the individual subjects. We instead encode each feature as a Gaussian mixture model across subjects, using expectation maximization to fit the GMM. The GMMs are then fully parameterized by the means, standard deviations, and mixing parameters pi, and this is the only information which must be shared, as they are estimated across the population, they contain no information about individuals. We can then adapt the model for a given target site. We assume an unlabeled target site, and so the model cannot just be fine-tuned. Instead, we will align the feature distributions between the source and target sites. Thus, we take the source-trained model and fit a GMM to the target features, creating estimates of the target parameters. We then fine-tune the feature extractor to align the features using a modified Bhattacharya distance, which calculates the distance between 2 distributions. It has a closed-form solution for 2 normal distributions, and so we adapt this for the more general GMM setting. The GMM fitting and loss function are fully differentiable, and so it can be trained end-to-end. At inference time for the target site, we then simply take the fine-tuned feature extractor and the source-trained label predictor to create the label predictions. This ensures that images with the same feature embedding have the same prediction, regardless of whether they are from the source or target site. We first tested our method for classification, where the majority of source-free domain adaptation methods have been applied. We used the organ AMNIS data and applied 4 domain shifts designed to simulate the shifts we'd expect when working with medical images, changes in contrast and changes in noise. Our approach outperformed the existing methods for SFDA, especially when only a small batch size was used. As medical images are generally very large, this is a very likely scenario. Visualization of the features via PCA shows a clear improvement in alignment between the source and target features for the different domain shifts. We then removed whole classes from the target data during training to create extreme imbalance in the labels. SFHarmony performed well despite the imbalance. We also simulated differential privacy by applying Laplacian noise to the weights before communication. Due to being able to calculate the GMM parameters prior to applying the differential privacy, the approach is very robust to the application of the Laplacian noise. We also applied the approach to segmentation and regression tasks without any change to the approach. For details, please see the poster or paper. To conclude, we have presented SFHarmony, a flexible framework for source-free domain adaptation. The approach requires no changes to the source training and is applicable to a wide range of tasks and network architectures beyond medical imaging. More details in the code can be found by following the QR code.